In today's lecture, we will go through discussion on elementary integration formulas, which should not be called integration formula, rather antiderivative formula. We know that when we take the derivative of x or x plus some constant, the derivative of x is 1 and the derivative of constant is 0. So if you have to integrate 1, that means integral dx, then the result should be not only x, but x plus some constant, as the derivative of x plus any constant will be 1. So you know this for some time. If integrand, now we have this integral sign, then we have integrand, a function which is being integrated, and dx indicates with respect to what variable we are integrating. So when you are integrating only with respect to x, and the function is 1, the integral is x plus c. If the function is a constant function, then constant remain as it is, and the integral of 1 is kx plus some arbitrary constant. Similarly, we are familiar with the fact that the derivative of x power any number is number multiplied by x power n minus 1. That means the process of derivative is something like x for x power n. Power multiplied and power decreased. The reverse process should be what? That is the antiderivative. The antiderivative for x power n should be first increase the power and then divide the result by the increased number. Here we first multiply with the power and then decrease the power. This is the process of differentiation. So the process of anti-differentiation should be first increase the power, the last step taken first, and then divide by the increased power, that first step carried out last. And always we place an arbitrary constant. Now in this case, since n plus 1 appears in the denominator, so we note that n should not be equal to 1, minus 1. Now we have this antiderivative formula, dx upon x, and 1 upon x ka antiderivative is ln x. So we should be familiar with the fact that y, the derivative of ln x is equal to 1 upon x. Why it is so? If you know, that's perfectly all right. And then antiderivative of 1 upon x is indeed ln x plus c. Now, whenever in any antiderivative is written in terms of ln mod x, or in terms of the function ln, the natural log, mod x is placed because log of x is not defined Sorry, my pen is not working properly. Lnx is not defined for all x, 0 and negative. That is why we have to force the argument of lnx in the result of the derivative in the mod, that is only positive values. But there is no such restriction here, uh, except that we are directly using lnx, and we know that lnx is not defined for 0 and negative, and the result is this. The question is that why result of the derivative lnx is this? For that, a simple rule which is deduced from the properties of log. This is log base to e. The properties of log tell us that this means x is equal to e raised to power y. And when you consider dx by dy, and if you know that the derivative with respect to y of e power y is equal to e power y, so we write down dy by dx is equal to 1 upon e power y, that is 1 upon x. This is one reason that we write down log derivative of ln x is equal to 1 upon x. And there are other reasons also if you use the first principle. So e power x, the derivative, we know that it's e power x, so its antiderivative should also be e power x. And if instead of e power x, you have b power x, then the antiderivative is b power x divided by this. The reason for that, when you consider y is equal to b power x, and you can write down this as ln y, that means apply ln on both sides. So the right side becomes x times ln of b. And now you are up against ln y is equal to x ln b. If you differentiate this with respect to x, the derivative of ln y will be 1 upon y, then dy by dx, the chain rule that you may have studied. Here ln b is constant, the derivative of x is 1. That means the result is dy by dx is equal to y times ln b, and as y was b power x, that means the derivative of b power x is equal to b power x into ln b. So what we do in the differentiation of b power x, b power x as it is, and it is multiplied by ln b. That is why when we take antiderivative, b power x remain as it is. Instead of multiplying b power x with ln b, which we did in the differentiation, we divide by ln b as we are going through a reverse process. Now, trigonometric functions, and you know the derivative of sine is cosine. Let me discuss these things separately. Derivative of sine is equal to cos x. Now, the result is cos x. So when I will be writing down antiderivative of cos x, my result should be sine x plus c. If the derivative of cos x is equal to, we know that it is minus sine. And when I write down the antiderivative of sine, it should be cos x, but a negative sign should also be there. Now, these derivative formulas can be proven using the first principle as the previous formulas, all that I'm discussing. But from this point onwards, if we go to take the derivative of tangent x, we don't take this derivative using first principle. Instead, we evaluate this derivative using the definition of tangent, that is sine upon cos, and apply u upon v rule that we discussed in the review. And when we apply that, we have denominator is squared, denominator as it is, derivative of the numerator cos x minus numerator as it is, and derivative of the denominator minus sine x. So that becomes cos square x plus sine square x divided by cos square x. You know that cos square x plus sine square x is equal to 1. So the result comes out to be 1 upon cos square x, which you write down as secant square x. So the derivative of tangent function, cotangent function, secant function, and cosecant function are obtained in the same way. So whenever I have to think about a corresponding antiderivative formula, तो antiderivative ना मैं tangent का लिखता हूँ, ना मैं cotangent का लिखता हूँ, ना secant का in the beginning. I see that the derivative of tangent is secant square, so that means antiderivative of secant square has to be tangent x, of course, plus c. Now, the secant square antiderivative is tangent x, cosecant square antiderivative is minus cot, because cot का derivative minus cosecant square है. Secant का derivative secant into tangent है. So antiderivative of secant into tangent should be secant. Derivative of cosecant is minus cosecant into cotangent. So the antiderivative of cosecant into cotangent should be minus cosecant plus. Yes, we write down derivatives of tangent, antiderivatives of tangent and cotangent, but for that, we need a technique. And let me introduce this technique for these two particular integrals, but we will consider the technique in more detail later on. So somebody asked me to write down the antiderivative of tangent x. I know that tangent x itself is not the derivative of any elementary function. So what I do, I consider this as sine x upon cos x, and I make a substitution for the denominator function. T is equal to cos x. That gives me the differential, or dt by dx is equal to minus sine x dx. Now that helped me convert this integral into what? I have in the denominator cos x, which has to be replaced with t, whereas in the numerator I've got sine x dx. Sine x dx is minus dt, and that makes it integral. What type integral? Integral dx upon x, which is log x. So I keep my negative sign as it is and write down log of t plus c. Now this result, that is integral of tangent x, can be written in two forms. One form is this, CBCD. T is equal to cos x plus C. But if I take this minus 1 into the power of cos, it become 1 upon cos, and 1 upon cos is secant. So we more popularly write it as secant of x. And technically, we should put mod because secant can attain negative values, secant can attain 0 values plus C. So that is why integral of tangent is a log of secant or minus log of cos x. Similarly, integral of cot x can be proved to be log of sin x, and using a similar procedure, you can do it yourself. Now, in this part, of course, we use two additional functions very frequently. One is written as sin h x. That means input is x. This is written as read as sin hyperbolic. The definition of this function is e power x minus e power minus x divided by 2. That means if I take the derivative of sin hyperbolic x, I have to take the derivative of this function. That means 1 upon 2 d by dx of e power x minus e power minus x. And that means 1 upon 2 e power x derivative as it is, e power minus x derivative minus e power minus x, so minus minus becomes plus. Now, what is this function? This function is called cos hyperbolic x. So cos hyperbolic x is defined as e power x plus e power minus x divided by 2. Now, what if I take the derivative of cos hyperbolic x, and we observe that 1 upon 2 derivative of this will result into e power x minus e power minus x divided by 2, and that is sin hyperbolic. So we come to the conclusion that when we take the derivative of sin hyperbolic, the result is cos hyperbolic. When we take the derivative of cos hyperbolic, it comes out to be sin hyperbolic. And that means, unlike trigonometric function, where derivative of sine is cosine and the derivative of cosine is minus sine, यानी cosine के derivative में change of sign आ रहा है, लेकिन यहाँ जो functions हैं, sin hyperbolic का derivative cos hyperbolic और cos hyperbolic का derivative sin hyperbolic. Similarly, when we write down the integral of sin hyperbolic, it will be cos hyperbolic. When we write down integral of cos hyperbolic, it will be sin hyperbolic. No change in sign. We can go on to find out the derivative of tangent hyperbolic, cotangent hyperbolic, secant hyperbolic, cosecant hyperbolic, and see what are their derivatives, and from there these derivatives are these antiderivatives are deduced. Now, out of these 4, 17, 18, 19, and 20, I will work out one of them, and at least 2 people are there in the class. I let them choose any number, 17 to 20, कोई एक जिसकी मैं डिटेल डिस्कस करती हूँ. Talha and Daulat are in the class. Somebody has selected a question 18. That is good. Uh, 18 means we have to talk about cot hyperbolic. Now, first of all, what should be cot hyperbolic x? Like trigonometry function, it has to be cos hyperbolic x upon sin hyperbolic x. And we have defined just a few minutes earlier, the cos hyperbolic is e power x plus e power minus x divided by 2, whereas sin hyperbolic x is e power x minus e power minus x divided by 2. Algebraically, this 2 cancels. Further, if I want to simplify it, it becomes this. Minus 1 upon e power x. If I take LCM in the numerator as well as denominator, this becomes e power x. So in the numerator, you have got e power 2x plus 1 upon e power x. In the denominator, you have got e power 2x minus 1 divided by e power x, whereas e power x cancel out. And the cot hyperbolic function in its simplest form is e power 2x plus 1 upon e power 2x minus 1. And now I attempt the differentiation d by dx of cot hyperbolic x, and I will be using u upon v technique. U upon v technique tells me e power 2x minus 1 raised to power 2, e power 2x minus 1 denominator as it is. The derivative of numerator 2 e raised to power 2x plus 1 minus u upon v में अब numerator remain as it is, and the derivative of denominator has to be written with 2 e raised to power 2x minus 1. Now, in this form, you see that it becomes a bit complicated. We could have gone into differentiation from this direct form. Anyways, let us try to simplify this. This implies d by dx of cot hyperbolic x is a complicated kind of thing. हम इसको algebraically जितना simplify कर सकते हैं कर दें. This multiplied by this 2 e raised to power 4x plus e raised to power 2x minus 2 e raised to power 2x minus 1, ये दोनों मल्टीप्लाई कर दिए. अब इन दोनों की मल्टीप्लिकेशन करनी है हमने. e power 2x into this, that means 2 e raised to power 4x, e power 2x into minus 1, 1 into 2 e raised to power 2x, 1 into minus 1. You want to write down this after opening, so I discourage you opening it at this point. I keep it as it is, and now I look into the numerator. 2 e raised to power 4x here is positive, but here it is negative, so this cancel out. E raised to power 2x here is positive, and here it is also positive. Minus 2 e raised to power 2x negative, and minus 2 e raised to power 2x negative. Minus 1 and plus 1, they cancel out. And what we are left with, e power 2x plus e power 2x, 2 e raised to power 2x, minus 2 e raised to power 2x, minus 2 e, so minus 4 e raised to power 2x divided by e power 2x minus 1 raised to power 2. Now, what can be done to reach the result that cot hyperbolic का डेरिवेटिव कोसिकेंट हाइपरबोलिक स्क्वायर आना चाहिए. तो cosecant hyperbolic x should be what? 1 upon sine hyperbolic. And 1 upon sine hyperbolic means e power x minus e power minus x divided by 2. So 2 upon e power x minus e power minus x. तो cos hyperbolic square x आने के लिए ऊपर मेरे पास 4 आना चाहिए था. So let me see that I have done some mistake or not. Because as a result of the derivative of cot hyperbolic, I should have cosecant hyperbolic square with a negative sign. But I don't see that this becomes this form. If I put square here, so cosecant hyperbolic square x should be this. So denominator is in the required form, but the numerator requires to be only one term that should be reduced to this. So I may have made some mistake. This into this positive, this into this positive, this into this negative, this into this negative. Now minus of the formula, e power 2x plus 1 as it is, and this, so product of these two, this into this positive, this into this negative, this number into this positive, this number into this negative. अच्छा जी, e power 4x तो कैंसिल हुआ, e power 2x ऐड हो गया, और this term seems to be a troubling term. This should not be here. हाँ भाई, $, can you find the mistake? Denominator is square, denominator as it is, derivative of numerator minus numerator as it is, derivative of denominator. जी, मिली मिस्टेक नहीं मिली? नहीं मिली? अब सर कर रहे हैं तो सही कर रहे होंगे, है ना? Denominator is squared, denominator as it is, derivative of numerator. When I take the derivative e power 2x plus 1, तो e power 2x का derivative तो आ गया. ये 1 कैसे बच गया? 1 should not be there. 1 का derivative 0. Minus derivative of the minus numerator as it is and derivative of denominator. जब मैं denominator का derivative लिखूंगा तो e power 2x का derivative तो ये आ गया. -1 का derivative 0 है, ये कहाँ से आ गया? So that was the mistake. So I write down derivative of cot hyperbolic x again. So I have a term of 2 e raised to power 4x minus e power 2x. From here, minus 2 into e raised to power 4x and minus what? e power 4x टर्म कैंसिल होगी, what we are left with, minus 2. So minus 4 e raised to power 2x. Now this is perfectly all right. How it is perfectly all right? This can be written as 4 upon e power x minus e 1 upon e power x raised to power 2, which then can be written as 4 upon e power x minus 1 upon e raised to power x raised to power 2, which then can be written as what? E power x goes above with power 2, so 4 e raised to power 2x divided by e power x minus 1 raised to power e power, sorry, ये जब मैंने LCM लिया तो ये 2x हो जाएगा. And now it is in the required form, minus 4 e raised to power 2x. A minus b whole square or b minus a whole square is same. So e raised to power 2x minus 1 whole square. And the result is now obtained as this. So cot hyperbolic x, the derivative आया minus cosecant hyperbolic square x. Now, since the derivative of cot hyperbolic x has come out to be minus cosecant hyperbolic square x, so in antiderivative of cosecant hyperbolic square x is equal to minus cot hyperbolic x. Similarly, you can prove the rest 3 of them. But of course, these are new functions. We have not dealt with these functions before. जिस तरह ट्रिग्नोमेट्रिक फंक्शंस के बहुत फॉर्मूले हैं, इसी तरह इन हाइपरबोलिक फंक्शंस के बहुत से फॉर्मूले हैं. Whenever we'll require them, we'll discuss them. Just as कि मैंने 17, 18, 19, 20 में से आपको एक प्रूफ करके दिखाया आपकी डिमांड पे. We can prove the rest, but using only the basic definition of sine hyperbolic and cos hyperbolic. Tangent क्या बनेगा? This upon this. Cotangent क्या बनेगा? This upon this. Secant क्या बनेगा? 1 upon cos hyperbolic. Cosecant क्या बनेगा? 1 upon sine hyperbolic. Just as this, cos hyperbolic is 1 upon sine hyperbolic. So these formulas can be proved. Then there is a list of algebraic functions, irrational functions, whose integrals are obtained in this form. I will consider some of them, choosing to prove these antiderivatives. I'll choose myself. For example, I need to work out integral dx upon square root of a constant square minus a variable square. I want to find it out what is this. Though I have written this as basic formula, but of course every basic formula requires to do proof. So ये भी substitution जैसे हमने पहले टेंजेंट को इंटीग्रेट करने के लिए सब्स्टिट्यूशन इस्तेमाल की थी. To obtain the integral of the tangent, we use a substitution. We will again use a substitution here. And we will discuss these substitutions in detail at a later stage. In this form, when under the root constant is positive and variable x square is negative. In this case, we always make the substitution x is equal to a sine theta. That gives me dx is equal to a cos a derivative of sine theta, cos theta, and differential of theta, d theta. Have you done substitutions of this type before? Even if you have done, I'll consider this repeated to remind you this technique. जब मैं ये सब कुछ करता हूँ तो मेरा जो ओरिजिनल इंटीग्रल है वो ट्रांसफॉर्म होकर किस शेप में आ जाता है? dx की जगह पे a cos theta d theta upon under the root a square minus x की जगह a square sin square theta. What happens now? The numerator is very simple. In the denominator, if I take x a square common, बाहर आके ये सिर्फ a रह जाएगा, and inside I will have only 1 minus sin square theta. This a cancel out, and what remains? In the numerator cos theta, d theta, what is there in the denominator? What is 1 minus sin square theta equal to? Talha, Daulat, do you have any idea what is 1 minus sin square theta is equal to? And what is cos square theta plus sin square theta equal to? ये 1 है तो 1 minus sin square theta किसके बराबर हुआ? What we are left with is cos square theta. So under the root you have got cos square theta. That means integral cos theta d theta upon cos theta only. So cos theta and cos theta cancel out, and we are left with only d theta. That means the antiderivative is only theta plus a constant. Our result is in terms of a variable which was introduced through this substitution. If you look at this substitution, this says that x upon a is equal to sine theta. And that means theta is equal to sine inverse x upon a. So ultimately, we come out with the result that dx upon under the root a square minus x square is equal to theta, that is sine inverse x upon a plus c. So sine inverse x upon a plus c यहाँ पे गौर करो कि लिखा हुआ है मॉड x मस्ट बी लेस देन a। उसकी वजह क्या है कि अंडर द रूट यू हैव गॉट a स्क्वायर माइनस x स्क्वायर। दिस शुड नॉट बी नेगेटिव। अगर a स्क्वायर की वैल्यू x स्क्वायर से ज्यादा हो गई, सॉरी x स्क्वायर की वैल्यू a स्क्वायर से ज्यादा हो गई, तो ये अंडर द रूट है तो ये कॉम्प्लेक्स हो जाएगा, और हम सिर्फ रियल फाइनाइट और यूनिक सिचुएशंस डिस्कस कर रहे हैं। Now, the proof of this I have done, and for the proof of this, I suggest that you make the substitution x is equal to a tangent theta and do it yourself. Number 24. Number 26, I suggest that substitute x is equal to a secant theta and do it yourself. But the rest of them, ये वाला रिजल्ट tan इनवर्स में आ रहा है, ये वाला रिजल्ट secant इनवर्स में आ रहा है, that means it's a problem of the same type. इसलिए आपको मैंने सब्स्टिट्यूशन बता दिया, काम बिल्कुल वैसे ही करना है जैसे हमने इसमें किया था. So now I will select one out of this 22 and 23. Which one you will prefer, 22 or 23? And it's 23. इसलिए कि इसके अंदर नेगेटिव आ. Okay. So let us go to look at this. What integral? Integral dx upon x square minus a square under the root. Now, whenever we have x square minus a square, there are various kinds of substitution that you can use. हमें trigonometry से लीड मिलती है कि 1 plus tangent square theta is equal to secant square theta और secant square theta minus 1 is equal to tangent square. एक लीड तो वहां से मिलती है, कहाँ से? ट्रिग्नोमेट्री से. एक लीड हमें हाइपरबोलिक फंक्शन से भी मिलती है, और वो मिलती है कि अगर हम हाइपरबोलिक फंक्शंस के फॉर्मूले में जाएं, cos hyperbolic square theta minus sin hyperbolic square theta is equal to 1. Now this formula can be proved using this formula for sin hyperbolic and this formula for cos hyperbolic. इन दोनों को अगर आप इसमें रखें तो सब कुछ सिंप्लीफाई होकर 1 रह जाएगा. And this makes me think about a cos hyperbolic square theta minus 1 is equal to sin hyperbolic square theta. Now, why I say that these are the two leads? Because here variable is squared minus constant square. यहाँ variable is squared minus constant. यहाँ variable is squared minus constant. For reasons, I select this path and try what happens. So I say that let x is equal to a cos hyperbolic theta, that will give me dx is equal to a sin hyperbolic theta d theta. And that will make this integral look like what? Dx replaced by a sin hyperbolic theta d theta upon under the root, in place of x, a square cos hyperbolic square theta minus a square. And that means I'll keep numerator, which is simple as it is. In the denominator, under the root, a square is common. अगर मैं इसको कॉमन लेके बाहर निकाल दूं तो it will be only a under the root cos hyperbolic square theta minus 1, which is equal to sin hyperbolic square. So what I get is this cancel out, and the result is in the form result तो नहीं, लेकिन next step will be in the form cos hyperbolic square theta minus 1 is equal to sin hyperbolic square theta. And that means you are left with only 1 because this cancels d theta, and that means the integral is theta plus c. Now what is theta? We substituted this. So before I finally write down the result in terms of the original variable x, let me explore this. The substitution. X upon a is equal to cos hyperbolic theta, whereas cos hyperbolic theta is equal to e raised to power x minus plus e raised to power minus x divided by 2. And that makes 2x upon a. What I've done is taken this 2 on this side and e power x plus 1 upon e power x. Taking LCM, this becomes e power x, e power 2x plus 1. So I have an equation which is of what form? E power 2x plus 1 upon e power x is equal to 2x upon a. I have to find out a relation between theta and x upon a. वो तो मैं भूल ही गया. मैं तो थीटा को इसमें यहाँ पे आ गया और थीटा गायब कर दिया था मैं. कॉस हाइपरबोलिक थीटा है ये थीटा है, ये थीटा है, ये थीटा है, ये थीटा है. This is theta. This is theta. And now I see that I have, if I take this e power theta on the right hand side, e power 2 theta plus 1 is equal to 2x upon a into e power theta. You will find that this is becoming complicated. It has these substitutions and these integral formulas. जो अक्सर किताबों में फॉर्मूला के तौर पे दिए होते हैं, इनके प्रूफ्स जो हैं वो दे आर नॉट ऑलवेज वेरी सिंपल, लाइक जो हमने किया था पहले वाला और साइन इनवर्स आ गया था. और यहाँ भी हम बड़े खुश हुए थे कि थीटा प्लस सी आ गया, तो थीटा साइन इन कॉस, यानी आई कुड राइट डाउन व्हाट थीटा इज इक्वल टू कॉस हाइपरबोलिक इनवर्स x upon a plus c. ये हो गया रिजल्ट. तो अब मैं क्या कर रहा हूं? मैं कह रहा हूं नहीं भाई, किताबों में जो फॉर्मूला लिखा हुआ है वो ये लिखा हुआ है. हाउ इज इट इक्वल टू व्हाट आई हैव अराइव्ड इट? सो आई एम कन्वर्टिंग इट टू दैट फॉर्म. अब देखो e पावर थीटा ये स्क्वायर्ड है, जबकि इधर से आ रहा है माइनस 2 इंटू एक्स अपॉन ए ई पावर थीटा प्लस 1. What kind of equation is this? This is a quadratic equation in e power theta. ये variable है, variable squared minus 2 times something into variable plus 1 is equal to 0. अगर मैं इसको e पावर थीटा के लिए सॉल्व करूं तो मुझे अपना क्वाड्रेटिक फॉर्मूला याद करना पड़ेगा x is equal to minus b plus minus square root of b square minus 4ac divided by 2. So this is my x of this equation or unknown of this equation. A is equal to 1, b is equal to minus 2x upon a, and c is equal to 1. So the unknown squared minus constant into unknown plus 1 is the quadratic equation on which I am applying quadratic formula. So minus of b का मतलब है इसका negative 2x upon a plus minus square root of b square, that means 4x square upon a square minus 4ac. So minus 4 into 1 into 1 whole divided by 2a. Oh. Now where do I reach? 2x upon a plus minus under the root 4x square upon a square minus 4 whole divided by 2. So I write down divided by 2, तो ये 2 कट जाएगा, x upon 2 लिख जाएगा. This was plus minus 1 upon 2 ये वाला, and what else there is in the under root 4 common है, 4 common से बाहर निकल के आएगा 2 हो जाएगा, और बाकी जो बचेगा सॉरी what is this x upon a x square upon a square minus 1. ये वाला 2 भी कैंसिल हो गया, and now I have got x plus minus, इसमें एलसीएम लूं तो बनेगा क्या, x स्क्वायर माइनस a स्क्वायर डिवाइडेड बाई अंडर द रूट के में a स्क्वायर, तो रूट से बाहर निकाल दो तो वो भी है, तो इसके नीचे भी है और इसके नीचे भी है. So I have reached e power theta is equal to x plus minus under the root x square minus a square upon a. But what was the required result? We are working out this one. Required result was in the form ln x भी आ गया, ये क्या आ गया, a minus x square minus a square. हमने क्या शुरू किया था? Did we do 23? Yes, we did 23. We substituted as x is equal to a sine a cos hyperbolic theta. And it's not good. My formula cos hyperbolic square theta minus sin hyperbolic square theta can be written in what form? Cos hyperbolic square theta minus 1. ये इधर आएगा तो ये माइनस होगा, या मैं इसको लिख सकता हूँ cos hyperbolic square theta is equal to 1 plus sin hyperbolic square theta. That means wherever I have used this, it should have been used instead of cos hyperbolic theta, I should have used sin hyperbolic theta. So जो ये रिजल्ट बन रहा है वो एक्स स्क्वायर माइनस ए के लिए नहीं बल्कि एक्स स्क्वायर प्लस ए के लिए बनता है। एक्स स्क्वायर प्लस ए के लिए ये ठीक है, ये सब्स्टिट्यूशन what else the minus sign can be given to sin hyperbolic square theta is equal to, सही तो किया है, sin hyperbolic स्क्वायर कर दिया तो पॉजिटिव हुआ और 1 इधर आया तो माइनस हुआ। I did it correct. This is x square minus a square. Cos hyperbolic square theta minus 1 is equal to this. Everything is all right. Right. Everything is all right. Minus b, okay. Minus 4ac is all right. बस यहाँ का एक साइन और चेक कर लें। cos hyperbolic theta में पॉजिटिव आता है और हमने सब्स्टिट्यूट किया था cos hyperbolic theta ही किया था। Yes. Everything is all right. I think the formula that's written there is not correct. Because we are obtaining x square minus a square. This is not correct. Now, there are two issues. एक issue तो मैंने डिस्कस किया, हमारे पास x square minus a square आ रहा है तो लेकिन हमें फॉर्मूला सही नहीं होगा। दूसरा इशू ये है, now both the results are acceptable obtained from quadratic formula plus or minus, plus or minus। ये वाला नेगेटिव तो उड़ गया था मगर ये प्लस माइनस अल्टरनेट्स मौजूद हैं। अगर मैं इस इक्वेशन पे ln लगाऊं, ln of e power theta, so that will be ln of x plus or minus, both are acceptable, divided by a plus c, log of e power theta, so that becomes theta log e, and log e is 1, and our result theta is ln mod x plus under the root x square minus a square plus c. Note that I have skipped writing down divided by a because log of b upon a is equal to log of b माइनस लॉग ऑफ ए, क्योंकि डिनोमिनेटर जो है वो कांस्टेंट है, ये कांस्टेंट होगा और ये कांस्टेंट इस कांस्टेंट में एब्सॉर्ब हो जाएगा। सो वी राइट डाउन द रिजल्ट लाइक दिस, वेयर वी हैड रीच्ड एज अ रिजल्ट वाज ए। सो नाउ ए वाज द रिजल्ट फॉर दिस इंटीग्रल, सो वी राइट डाउन द cumulative result as ex upon square root of x square minus a square is equal to ln of x plus square root of x square minus a square plus c. So whatever error is there, I'll recheck and मैंने वैसे तो याद पड़ता है किताब से लिए थे formula, but the structure says that x square minus a square result में x square minus a square ही आना चाहिए था, a square minus x square नहीं आना था. Similarly, we can approach this. We can approach this, and we can approach this. 25, 27, and 28. You select one of them, and we go trying to prove this. 25, 27, 28. 24 और 26 के लिए मैं आपको हिंट दे के कह चुका हूं कि आप खुद कीजिए. 25, 27, and 28. इनमें से कोई एक सेलेक्ट कर लीजिए. Oh, there is another shown. Iqra is there. Okay, arbitrary 25, 27, 28. Select one. 28. Okay, ji. What is the form of 28? A square minus x square है और बाहर है x. Let me confirm. A square minus x square. What should I use as a substitution? Constant minus variable square. We have done it before. Here I will try the simple a sin theta. हो सकता है मैं स्टकअप हो जाऊं कहीं पे. मुझे जो रिजल्ट आना है दैट इज इन द फॉर्म और बड़ा मजेदार फॉर्म है. Let us try this substitution. There is dx will be a cos theta d theta, and the integral transforms to what? dx की जगह a cos theta d theta divided by x की जगह a sin theta under the root a square minus x की जगह a square sin square theta. This a cancels. Cos theta d theta. In the denominator, I have got sin theta. A square taken common from the square root is a under the root 1 minus sin square theta, and 1 minus sin square theta under the root is cos theta, so the cos theta cancels with this. And what I am left with is 1 upon a integral d theta upon sin theta. But what is 1 upon sin theta in trigonometry? Anybody remember? You should remember this. This is the last of the trigonometric function, cosecant theta. This implies my integral that I started with, dx upon x under the root a square minus x square, has transformed into 1 upon a integral cosecant theta d theta. Although we have in our list, where is cosecant? Is there any cosecant? No, because cosecant is not the derivative of anything. So we don't have anything for cosecant. हाँ, कोसिकेंट का डेरिवेटिव माइनस कोसिकेंट इंटू कोटेंजेंट है, ये हमें पता है. तो अब कोसिकेंट का इंटीग्रल कैसे लिखें? कोसिकेंट एक ऐसा फंक्शन है जिसका जो किसी फंक्शन का डेरिवेटिव नहीं है, लिहाजा इसका एंटी डेरिवेटिव लिखना सिंपल नहीं है. दिस इज नॉट सिंपल. So we need some technique, a technique. I have mentioned that here we will learn some new technique, here we will learn some new technique. Why those techniques are required? One of the major reason is that we are stuck up here. So let us see what is the derivative of cosecant theta. If you remember, it is minus cosecant theta. What's the derivative of cot theta? It is minus of cosecant square theta. That appear here. Cot theta का डेरिवेटिव माइनस कोसिकेंट स्क्वायर है और कोसिकेंट का डेरिवेटिव माइनस कोसिकेंट कोटेंजेंट है, जिसकी वजह से ये एंटी डेरिवेटिव फॉर्मूले यहाँ पे लिखे हुए हैं. उनको हम प्रूफ नहीं करते, लेकिन ये हमारी ऑब्जर्वेशन जो है इसको सॉल्व करने में मदद करेगी. कैसे मदद करेगी? Let us see what I do. Now, don't ask me आपको ये कैसे पता चल गया. This is one of the techniques that we have to learn, and the details will follow later. Multiply and divide by cot theta into cosecant theta. किस चीज को? इसको. So that will make, अब मैं सिर्फ ये लिख रहा हूँ, इंटीग्रल कोसिकेंट थीटा था जिससे मैं लड़ रहा था. I was up against solving this integral, जिसके लिए मैंने कहा कि इसको मल्टीप्लाई और डिवाइड कर दें cot theta not exactly this. Plus upon cot theta plus cosecant theta d theta. And then I observe that numerator is a special form. Cosecant into cosecant. Cosecant is square theta. Cosecant into cotangent. What's the denominator? Denominator में I've got cot theta plus cosecant theta. Now it is a special form, and I look into the derivatives of these two functions. Cot का derivative minus cosecant square, और cosecant derivative ये क्या मैंने लिख दिया? Cosecant का derivative क्या है भाई? Minus cot into cosecant. यहाँ पे cot भी. So do we have similar results? Cotangent का derivative minus cosecant square और cosecant का derivative minus cosecant into cotangent. They are available, but negative sign is not there. Apart from negative sign, this is all right. So I introduce a negative sign outside the integral and negative sign inside the integral. Divided by cot theta plus cosecant theta. And now I look at an interesting pattern and I say that let t is equal to cot t plus cosecant t. That makes dt look like what? Derivative of cotangent minus cosecant square x theta, derivative of cosecant minus cosecant theta into cotangent theta d theta. So I see that numerator is exactly this and denominator is exactly this. So that means my integral is now in the form of dt upon t. And I can write down the result as ln of t plus c. हाँ भाई कहाँ पहुंचे थे? We were stuck up here. और कोशिकेंट का एंटी डेरिवेटिव लिखते हुए हमने सब चीजें साथ रखी सिवाय 1/a. So 1/a is there. Now there are still some problems. One problem is minus 1/a ln of t. And what is t? T is cot theta plus cosecant theta. मगर थीटा की सब्स्टिट्यूशन हमने क्या की थी? थीटा की सब्स्टिट्यूशन हमने ये की थी. यानी ओरिजिनल वेरिएबल x was a sin theta. जबकि रिजल्ट हमारे पास आ रहा है माइनस कॉस स्क्वायर कोसेकेंट स्क्वायर. कैन आई राइट डाउन दिस माइनस कोसेकेंट स्क्वायर? नहीं, ये थोड़ी आया, ये आया टी, ये वाला. कॉट की जगह में कॉस थीटा अपॉन साइन थीटा लिख सकता हूँ. एनी प्रॉब्लम? नो प्रॉब्लम. कोसेकेंट थीटा की जगह मैं 1/sin थीटा लिख सकता हूँ. परफेक्टली ऑल राइट. प्लस सी. जबकि साइन थीटा असल में x/a है. Sorry, if sin theta is x/a, what should be cos theta is equal to? Cos theta should be equal to 1 minus sin square theta. इसका मतलब है it should be 1 minus x square upon a square. चलो भाई, सारा मसाला तैयार हो गया. माइनस 1/a ln ऑफ, दोनों के नीचे साइन थीटा है. साइन थीटा इज x/a. कॉस थीटा की जगह स्क्वायर रूट ऑफ 1 माइनस x square upon a plus 1 plus c. And the last step, minus 1/a ln, इसको ये a स्क्वायर 1 माइनस एक्स स्क्वायर अपॉन ए स्क्वायर अंडर द रूट. जब मैं इसमें एलसीएम लूंगा तो इट विल बिकम a स्क्वायर माइनस एक्स स्क्वायर अपॉन ए. को एलसीएम लूंगा तो ये a हो जाएगा. a स्क्वायर माइनस एक्स स्क्वायर डिवाइडेड बाई स्क्वायर रूट ऑफ a स्क्वायर. तो a ये नीचे आ गया, x अपॉन a पहले से था, प्लस c. तो ये और ये कैंसिल हुआ and we reach the result that starting with 28 dx upon x times a square minus x square, the integral is 1 upon minus 1 upon a ln of square root of a square minus x square plus a divided by x plus c. And there we go. This is the result. इसमें a पहले लिखा है, स्क्वायर रूट बाद में लिखा है, but that doesn't mean anything. Now 25 and 27. 25, and you can work with x is equal to a sine theta. In 27, you can work with x is equal to a tangent theta. But let me tell you, the not simpler than that. These proofs, if not very difficult, then not very or simpler than these. These will be as complicated as these proofs. With that, I conclude today's discussion, and I have just discussed familiar integrals as first part for principles of integral evaluation. From very simple integrals to very complicated integrals, जिनको हम कह रहे हैं some familiar integrals. But how we work out more complicated, we need to learn few techniques. I have here exercise 7.1, almost all solved in detail, but I don't think I'll share the complete solution of the exercise 7.1. You go through exercise 7.1 as early as possible. Book मैंने share कर दिया आप लोगों से, and you can seek help from the book. I will, of course, share with you this page of some familiar integrals. I'll share with you these proofs of some of them after putting appropriate numbers to each proof that I've discussed. Okay, with that, I terminate today's session.
Hello, sir. Assalamu alaikum.
Wa alaikum